Hello everyone, welcome. I am Volk and I am going to speak about lower bounds for matrix factorization. This is a joint work with Mrinal Kumar from IIT Bombay. I'm going to do something slightly unconventional and begin this talk with an open problem. So the problem we're interested in is finding an explicit n by n matrix A, which cannot be written as a product of two sparse matrices. So whenever you have this equation A equals B times C, it can't be the case that both B and C are sparse. A sparse matrix is just a matrix with mostly zeros, and I'm vague on purpose about which exact parameters are interesting right now. For convenience, let's assume A is a square matrix n by n. It's not that crucial, it just helps to have one less parameter around, and then B and C can be rectangular of the appropriate dimension for the multiplication to make sense. As usual in complexity theory, when we say we want to explicitly construct a matrix, what we really mean is a family of matrices, either one for every n or for infinitely many n's. This is interesting over every field, as complexity theorists we are maybe more used to F2 or other finite fields, but this is also interesting over the rational or complex number, and in fact it could be easier the larger the field gets. Non-explicitly, most matrices have this property. So for a random matrix, it will be the case that you cannot write it as a product of two sparse matrices. This is just a counting argument over finite fields, and over infinite fields you need just a slightly more sophisticated dimension argument. The more general version of this problem is to find a matrix A which you cannot write as a product of D sparse matrices. For this talk, think of D as some constant. Alright, that's the problem. So now you can ask, why is it interesting? Well, the first reason is that it's just a very natural question, but it turns out that this also comes up in multiple areas of computer science. So I will now give some examples and explain the motivation for us to study this. The first motivation comes from algebraic complexity theory when we consider arithmetic circuits that compute linear transformations. So think of a linear transformation that sends x to a of x. Here x is a length n vector and a is an n by n matrix, and it turns out that such circuits are, without loss of generality, linear circuits. So what is a linear circuit? Here I will give a definition by a picture. A linear circuit is a circuit that only uses linear operations, which are addition and multiplication by scalar. So here you can see we have only addition gates, and each addition gate computes a linear combination of its children. The coefficients of the linear combination are written on the edges. Each edge has a label which is a scalar in f, and I didn't put them in the picture, but they are there. So like many circuit classes, when you first try to understand them, it's useful to consider bounded depth circuits. And let's assume also, without loss of generality, that the circuit is layered. So here we have an example of a depth 2 circuit. There are three layers: the bottom layer, which is the input layer, the middle layer, and the top layer, which is the output layer. So now it's just a matter of thinking about it for a few moments to realize that if you label by C the adjacency matrix of the subgraph between the bottom and the middle layer, and if you label by B the adjacency matrix of the subgraph between the middle and top layer, then what the circuit computes is the composition of the linear transformation given by C and B, which is B times C. So the connection to what we saw earlier is that the depth of the circuit corresponds to the number of matrices in the factorization, and the sparsity of the matrices correspond to the number of edges in the circuit. This is in fact a direct correspondence, so saying that a matrix can be factored into a product of two sparse matrices is exactly like saying it has a small depth 2 linear circuit, and this is also true for any constant depth d. Just to give some overview of the playing field here, clearly every matrix has a circuit of size n squared, even a depth 1 circuit of size n squared, and it's also very easy to prove a lower bound of n just by giving a linear transformation that depends on all the variables. So the whole game here is really between n and n squared. A very related concept, which was in fact defined in the same context, is the notion of matrix rigidity. So this is a famous theorem of Valiant, which says that if A is a matrix, or more precisely a linear transformation that has a linear circuit of logarithmic depth and linear size, then A can be written as a sum R plus S, where R has a very low rank little o of n, and S is a very sparse matrix. It has sparsity at most n to the 1 plus epsilon. A matrix which cannot be written in this form is called a rigid matrix. As a corollary to Valiant's theorem, we can show that if A can be decomposed as R plus S if it is not rigid, then you can take this sum decomposition and convert it into a product decomposition, so you get a depth 2 linear circuit of size little o of n squared. What it means is that if we could get the best possible lower bounds for depth 2 circuits, an omega n squared lower bound, then we would in fact get superlinear lower bounds for logarithmic depth circuits, which would be very significant. What this shows is that depth 2 is stronger than maybe one might initially imagine, because even in non-trivial size little o of n squared, it can compute all transformations with logarithmic depth and linear size circuits. This is actually a common phenomenon in algebraic complexity, and we usually call it depth reduction results. And there are several other similar theorems for general polynomials. What they show is that you can take a general small circuit and compress it to very shallow depth, so that very good lower bounds for very shallow circuits will in fact prove strong lower bounds for general circuits. Now, there is also a sort of converse for this theorem proved by Pudlak, and what it shows is that if A has a very small depth 2 circuit, then it is in fact not rigid. So this is a theorem that converts the product decomposition into the sum decomposition. But what I think is the take-home message from all of this is that proving n to the 1 plus epsilon lower bounds for depth 2 circuits is a necessary step towards proving rigidity, because it is implied by rigidity, so we might as well start by proving that, and this is what makes the model very interesting to study. So this problem of finding a matrix which cannot be factored as a product of two sparse matrices also comes up in the area of proving lower bounds for data structures. And there are many models here, but I'm going to focus on a model which is called dynamic data structures in the group model. And here we imagine we have an update algorithm U and a query algorithm Q, and they are both linear functions. So think of an input X as specifying weights to some n elements. So now we can apply U to update the weights and store them in some database, and then we can apply Q to query the updated database, and we can continue to apply them again and again. Now we can observe that the sparsity of Q and U roughly corresponds to the average case update and query time of the database. If a matrix is very sparse, then most rows are mostly zeros, and then we can apply these operations very quickly. So a matrix which can't be factored this way into a product of two sparse matrices corresponds to a hard database problem. Either the update time or the query time must be large. Now, of course, nowadays no talk is complete without mentioning machine learning. And it turns out that this problem of factoring a matrix into a product of two sparse matrices also comes up there. Of course, they are usually more interested in algorithms than in lower bounds, and they are usually also fine with approximating the matrix and not computing it exactly. But I will just briefly mention that they study things like algorithms for non-negative matrix factorization or sparse dictionary learning, which are somewhat related. And this problem also comes up in the analysis of deep neural nets. So a neural net is really like a linear circuit, except each gate, after computing the linear function, also applies some nonlinear function to the result. So now I'm going to tell you what is known about lower bounds for depth 2 linear circuits or depth D linear circuits. Well, the good news is that there are known superlinear lower bounds, but they are only barely superlinear. They are all based on lower bounds on the number of edges in a certain class of graphs called superconcentrators. So I will not define what a superconcentrator is. There are certain graphs with very good connectivity properties, but it is very easy to show using some simple rank argument that for some explicit matrices, the graph of every circuit computing them must be a superconcentrator. The harder part is now to show that every superconcentrator must be large, and this was intensely studied in the past, and today we know how to prove this theorem that every depth d superconcentrator has size at least n times lambda d of n, and for constant d, this function lambda d goes to infinity with n, but very, very slowly. So I have here some examples. When d equals 2, lambda 2 is log squared n over log n. For d equals 3, it's log n, and then 4 and 5, it's log star, and it deteriorates very, very quickly. Another thing is that we know that when d equals log n, there are already linear-sized superconcentrators, so this method cannot give superlinear lower bounds for log depth circuits. And also for bounded depths, we know that these lower bounds are tight. So for every d, there is a matching upper bound, and there exists a superconcentrator of that size. And what that means is that superconcentrators have really given us everything they could have given. So we really must find a different method in order to prove a better lower bound. There are also some lower bounds known for more restricted models of linear circuits, so let me give a few examples. The first example is the model of monotone circuits. A monotone circuit, let's say we are computing over the real numbers, is a circuit that can only use positive coefficients. So in this model there can never be any clever cancellations, and that makes them rather weak and also easier to analyze, and indeed there are almost optimal lower bounds known for monotone circuits, even without restriction on the depth. Another model, which is very natural, is the model of circuits with bounded coefficients. So now again, let's assume we are computing over the real numbers or over the complex numbers, and the circuit is only allowed to use coefficients with absolute value at most 1, or some other constant. So for this model, Pudlak proved lower bounds of omega d times n to the 1 plus 1 over d, and you can see that for any constant d, this is much better than the lower bounds we can prove for general circuits. Another interesting result, which is very relevant to this work, is this result of Shoup and Smolensky, who proved similar lower bounds for general depth d circuits, but the matrices for which the lower bound holds are not explicit, they are only what I call here semi-explicit. And what it means is that they are very easy to describe, they have very succinct mathematical description, but they are not explicit in the complexity theoretic sense of the word. They contain irrational numbers, so there's no algorithm that really writes down the entire matrix in polynomial or even in finite time. So one example of a matrix like that is take any n squared prime numbers, for example the first n squared prime numbers, let's index them by pij, and then set aij to be the square root of pij. So you can see you get these irrational numbers, and what we would really want for complexity theoretic explicitness is matrices with small integer entries or rational entries with small numerators and denominators. Alright, so now let me tell you what we do in this paper. Our first result is a deterministic construction of matrices which require large depth d linear circuits. So unfortunately we don't do it in polynomial time, we do it in time 2 to the n to the 1 minus 1 over 2d, and the lower bound we get is n to the 1 plus 1 over 2d. The constant 2 here is not that important, but it's there for convenience. It can be replaced with a smaller constant. Now the point here is that if we could construct rigid matrices with very good parameters, like the best parameters we can hope for, then such lower bounds will follow. But the problem is that we don't know how to construct rigid matrices with such parameters, even in much larger complexity classes like E with an NP oracle. So E is time 2 to the order n. So it's quite easy to construct such matrices in time 2 to the n squared, but we don't know even 2 to the order n. And we are able to do it in a much smaller complexity class by arguing directly about circuit size and not about rigidity. Our second set of results concerns restricted model of depth 2 circuits, so I hope I convinced you that depth 2 circuits are important, and we consider restricted models that correspond to many of the common ways that people factor matrices. So there are many common matrix decompositions like Cholesky and QR and LUP and so on, and we consider circuit models that are restricted but generalize these common ways to factor matrices, and we proved optimal quadratic lower bounds for these models. Let's see now some of the proofs or the ideas behind the proofs of the results in this paper. So let's begin with the lower bounds for general depth D circuits. So here imagine that the matrix contains elements from an extension field K of some ground field F. So now it's not very hard to observe that if A has a depth D circuits of size S, then A is in the image of some polynomial map with S variables with coefficients from the ground field F. In fact, it only has 0, 1 coefficients. And since this is the case, it's quite easy to show lower bounds for matrices that have many algebraically independent entries. For example, n squared algebraically independent entries. But this is not very satisfying because these are not the lower bounds we are looking for. We want lower bounds for explicit matrices. So the main observation in the paper of Shoup and Smolensky is that bounded depth circuits, in some sense, can't really distinguish between truly algebraic independent entries and the entries that are sufficiently, what I call here in quotes, algebraically rich. So this is some precise notion which I will define in a second, but this enables them to prove lower bounds for matrices that have algebraic numbers. Unfortunately, they are still non-explicit, as I showed you earlier. There's also a version of this argument that works for matrices with very large integer entries. This is still not explicit just because these integers are doubly exponentially large. So let's see the formal definition of what this algebraic richness means. So suppose A is an n by n matrix again over an extension field K of a ground field F, and let's denote by pi t of A the set of all products of t distinct entries of A. Each element of pi t of A is an element of the field K, and we also think of K as a vector space over F. Now let's define gamma t of A to be the dimension over F of the subspace which is spanned by those elements in pi t of A. So again, pi t of A is a set of elements of K, but we also think of it as a set of vectors over F. Then we take their linear span, and the dimension of this subspace is exactly gamma t of A. This is not exactly the original definition of Shoup and Smolensky, this is based on some later interpretation, but their main result is that this measure is small for low depth circuits, but it's large for this matrix A, which is defined as Aij being the square root of Pij for n squared distinct prime numbers, and there are many other similar matrices for which it works, but of course crucially it uses irrational numbers. So far I haven't explained the role of the parameter t here. Informally, t parameterizes how strong this measure gamma t is. When you take t larger, you can argue about circuits of larger depth, but there's some trade-off here of course, because when t is larger, it's also harder to construct matrices that have large gamma t. Fortunately for constant depth, it turns out that you can take t to be sublinear in n, which is what we are going to use. Our construction for a matrix which requires large circuits goes as follows. We start by constructing a matrix A over K, which is now the field of rational functions over F in a single variable y, And here each entry is a monomial in y, so aij would be y to the eij, and we would pick the exponents eij to ensure that the Shoup-Smolensky dimension of the matrix is large. We also have some reasonable upper bound on how large these exponents need to be. The problem here is that k is an infinite degree extension over f. So in the second step we just replace f of y with a large enough but finite degree extension of f, and we replace y with a primitive element of that extension field. Now over the rationals we don't want to use extension fields because again this will require us to use irrational numbers, so we need to replace the dimension argument with a counting argument which is slightly more messy but goes along similar lines. And now the matrix will be a matrix of integers which will be large but not too large, and the running time will be the same. The property we need the exponents to satisfy is that they will be what is called a T-Sidon set. This is a notion from algebraic combinatorics. What it means is that whenever you pick a subset of these elements of size t, and you sum the elements in that subset, the sum you will get will be different than the sums of all other subsets of size t. It's very easy to construct such a set if you just take distinct powers of 2, and then you would even have the stronger property that the sum of every subset is distinct. The problem is that then the size of the maximal element in the set will be too large. It will be 2 to the n squared. We want a set of size n squared. We only need the sum of every subset of size at most t to be distinct, and here it turns out you can do it with smaller numbers, and you can also construct it in the required time. This is the high-level description of the proof, and you can look at the paper for more details. But I want to move on to talk about the results for restricted types of depth-2 circuits, and as an example I will discuss the model of symmetric circuits. So recall that depth-2 circuits correspond to factorizations to a product of two matrices, and a symmetric depth-2 circuit is a circuit of the form B transpose times B. This is over the real numbers. Over the complex numbers it's more natural to take the conjugate transpose. So in the picture, a symmetric circuit is a circuit that remains the same if you reflect it along the middle layer. So you can imagine you are just given the bottom part of the circuit, and now you bring in a large mirror and you put it in the middle layer and you reflect it to get the top half of the circuit. This is over R. Over the complex numbers you also need a mirror that conjugates complex numbers. It should be clear from the definition that symmetric circuits compute positive semi-definite matrices, PSD matrices, and also every PSD matrix has a symmetric circuit computing it. In fact, it has many symmetric circuits computing it, and that's why it's interesting to prove a lower bound for this model. For this model of symmetric circuits, we prove optimal quadratic lower bounds. So we construct an explicit n by n PSD matrix A, such that every symmetric circuit for A has size omega n squared. And the proof for this theorem is pretty short. I will show it here on this slide. So let's see denote the Reed-Solomon code of length n, dimension n over 2, and distance n over 2 plus 1. Reed-Solomon codes are usually defined over finite fields, but there is nothing preventing us from using the same definition over R. If you don't know what the Reed-Solomon code is, it's not that important. The only thing you need to know is that it's a subspace of dimension n over 2, and it has the property that every non-zero vector in the subspace has Hamming weight at least n over 2 plus 1, and also it's explicit in the sense that we can construct a basis for this subspace in polynomial time. So let P be a generator matrix for this subspace. What it means is that the rows of P are a basis. And finally, set A to be P transpose times P. So A will be the matrix for which we prove the lower bound. And indeed, now suppose there is a different way to factor A as B transpose times B. And this matrix B is very sparse. It has fewer than n squared over 4 non-zeros. The first thing to observe is that the rank of A is n over 2. This is the dimension of the subspace. So B must have at least n over 2 non-zero rows, since otherwise the rank of B and also the rank of B transpose B is less than n over 2, so it cannot equal A. So since B has many non-zero rows, by an averaging argument, there must be a non-zero row that nevertheless has fewer than n over 2 non-zeros. And what this means is that there is a vector V in the dual of C, which is the set of vectors that are orthogonal to C, such that B times V is a non-zero vector. This is because there is this row that is non-zero but also has small Hamming weight, so this row cannot be orthogonal to all of C dual, otherwise it would have been in C. But it cannot be in C, its Hamming weight is just too low. So we have that BV is a non-zero vector, but now when we look at V transpose times A times V, well, on the one hand it equals V transpose times P transpose times P times V, and since V is in the dual of C, PV is 0, and this is 0, but V transpose times B transpose times B times V is just the L2 norm of the vector B times V, which is a non-zero vector, so it's non-zero, which is a contradiction. So it cannot be the case that you can decompose A as B transpose times B for a sparse matrix B. It might be a little bit hard to see the way I presented it, but this proof is actually a special case of a more general setting, which is related to polynomial identity testing. So let's define what is a heating set for matrices. A heating set for a class of matrices C is a set of n by n matrices, such that for every non-zero matrix A in the class there is some m in the heating set, such that the inner product between A and m is non-zero. And the inner product here is the standard inner product when you think of the matrices as vectors. So every possible class has a heating set of size n squared. This is the trivial upper bound. And the observation is that if you can construct an explicit heating set of size that's strictly less than n squared for a class C, then you get an explicit construction of a matrix which is not in C. The proof of this is very simple. You just find a non-zero solution to a set of linear equations. The linear equations come from the heating set, so we want to find a matrix which has zero inner product with all the matrices in the heating set, and if the heating set is small, then we can find a non-zero such matrix. And then since H is a heating set for C, it follows that B is not in C. This is exactly the same as the usual proof that heating sets for classes of polynomials give lower bounds for these classes, but it's just stated in a slightly different setting. So now of course the question is for which classes of matrices can we find small heating sets, and we give some examples in the paper. So now let's finish with some open problems. They are all related to proving lower bounds for linear circuits. The first problem is the following. We saw an n squared lower bound for symmetric circuits. And the natural question is it true that without loss of generality, the best depth-2 linear circuit for a positive semi-definite matrix is a symmetric circuit? Even if this is not strictly true, maybe it is approximately true in the sense that you can always convert any circuit to a symmetric circuit with a small blow-up, and then we could prove lower bounds for general depth-2 circuits just by first converting them to a symmetric circuit and then use the lower bound we have for symmetric circuits. So we don't have a lot of evidence in favor of this conjecture, and I don't know if there is any good reason to hope that it is true, but it will be nice to know either way. The second problem is more general, and it is to try to use this approach related to polynomial identity testing and to construct heating sets for various interesting classes of matrices. Of course, if we could do it for the class of matrices which are products of two S-sparse matrices, then we would get lower bounds for depth 2 circuits, but it's probably also possible to find other classes of matrices for which we can construct heating sets. And the last problem is the most general, which is again just to prove n to the 1 plus epsilon lower bound for depth 2 linear circuits in any way. As I said, I think this is a prerequisite towards solving more difficult problems in this area. Alright, that's all I have to say. Congratulations if you made it through to the end, and thank you for listening to my talk.